Okay, welcome back for more fun and games. It's variable separable again. Today, our last class, section 11.4, number 1, right on the homework page. Everyone know what page I'm on? 568, right? Okay, so find the solutions to the differential equations. So on exercises 127 with the given initial conditions. Let's do it. dp dt is given as negative 2p. And the initial condition is p of 0 is 1. How do you separate these variables so you can anti-differentiate both sides? It's, in this case, it's a cross multiply. It's not always a cross multiply, you're going to see. All right, so if we cross multiply, thinking of this as a fraction, we get dp equals negative 2p dt. Cross multiplying isn't enough here. Why? Because of the p's separated from the t's. No. So what's next? Divide by, well, the negative 2 isn't really an issue. I'll leave the 2 there. But the p's got to go. So divide by, you could divide by negative 2p, but then it makes it a complicated u sub later. I'm not going to bother with that. So divide by p, and you get a much easier situation to deal with. Alrighty, so what do you do next? Integrate both sides. I can put the integral here, I can put it over here. Really doesn't matter. And what do you get? What's the antiderivative of 1 over p dp? One? What? Were you here when we went over this homework today? We did this 100 times today already, this form. ln absolute p equals negative 2t plus a constant. All right, now that's an answer. That's a general solution. There's no derivative in here anymore, so that describes a function whose derivative they're talking about up here. But can you get p alone? Is there some way to get p as a function of t? Can you get rid of the ln? E to the, right? And then I'm going to say this. Are you ready? This might be new to you. What did I just do? I got rid of ln by raising both sides of the equation as powers of e. So the ln cancels to get p. And then e to the negative 2t plus a is, well, e to the negative 2t plus a, right? But is this the same thing? How do you multiply two powers with the same base? You add the exponents, right? The power is the whole thing, the exponent is this thing on top, right? This is the base, this is the power, the whole thing. This is the base, this is the exponent, the whole thing's the power, right? So if when you multiply two powers with the same base, you add the exponents, you could go backwards and say, look, this is just e to the negative 2t times some constant. I don't care that it's of the form of e to the a. I just care that it's some constant multiplying e to the negative 2t. This is going to be a common trick today to make life easy. Believe it or not, this is going to make life easy, okay? Now, can you resolve this constant? The constant of integration was a. This is not the constant of integration, but you need to resolve this constant. Wasn't there an initial condition? P of 0 is 1. So you're going to plug in what for p? 1. And you're going to plug in what for t? And 2 times negative 2 times 0 is just 0. And e to the 0 is, and 1 times b is b. So guess what? You got b already. So what's the final solution? Is that your final answer? Where's Regis Philbin when you need him? P of t is e to the negative 2t. That's what it is. Done. You have an exponential growth or decay function. Is it decay because this is negative? Why? Because the rate of growth of this population over time is directly proportional to the population you currently have. That is a definition of exponential growth. If the constant proportionality is negative, it's exponential decay. Okay? If you see this pattern, you know you should end up with this. But you still got to show all this work. Okay? We're going to practice this. This is slightly new today, but it's really based on stuff you know. This really didn't do anything new. Okay, let's try that again. How about number 2? Right, same idea. All right, number 2 says dp dt, I'm thinking that's probably a population over time, millions of worms in weeks or something, whatever, is directly proportional to the current population. Now this is a positive constant of proportionality, so would you expect exponential growth or exponential decay when you're done? Probably growth. Sort of like a banking problem. We have continuously compounded interest of 2%. Okay? And P of 0 is 20. All right, fine. So separate this for me. First step. Cross multiply. dP is 0.02 P dt. But that's not really separated. What do you got to do? Divide by P. dP over P is 0.02 dt. Now you can integrate both sides. And what do you get? ln absolute P equals 0.02 T plus a constant. All right, that's great. Now I could resolve the constant of integration using the initial conditions right now if I wanted to, but I think it's easier later on, so I'm going to do it later on. But it's not illegal to do it now. If you're careful, you'll get the right answer. What do I want to do next? E to the, right? Take both sides of this equation as powers of e, because that'll cancel this and get me p as a function of t, which is what I'm after if I can. Otherwise, I have an implicit solution. That happens. What should I write here, though? Some other constant. b e to the 0.02 t. Okay. Sorry, what? And that, right, so I'm calling it b. I don't care that it's e to the something, it's just a number. Now, they said p of 0 is 20, right? So let's figure out b. Plug in what here? E of 0 is 20, so who goes here, 0 or 20? 20 equals b e to the 0. And e to the 0 is? And 1 times b is b, so you got b already. It's like b for free. And you get p as a function of t is 20 e to the 0.02 t. So you have an exponential growth, sort of like compounded interest at 2% per year. Notice that the b is usually the initial population, p sub 0, like we called v sub 0, initial velocity. Usually in these problems, the initial population, p of 0, is b. Wasn't p of 0 20? In the previous example, wasn't p of 0 1? All right, this is a new pattern, exponential growth and decay differential equations. Yeah, Marie? You're going to have stuff like this. Or what? No, you should be able to do it this way. Yeah, I don't think there's a lot of instruction involved in the test now. Yeah, okay. Number 3. Just going to do a whole bunch of these for practice today. All right, dl dq. So we're looking for L as a function of Q if we can, is equal to L over 2, and L of 0 is 100. By the way, they don't always have to give you whatever at 0, right? It could be at 1 or something, whatever. But it's easy when it's 0. All right, so what do you do next? Cross multiply, yes and no. You could. I'm going to leave the 1/2 where it is. I'm going to say dl equals L over 2 dq. Now what? I find moving the constant to the other side just makes it harder to integrate later. So I'll leave the constant on this side. Usually that's a lot easier. But divide by L. The L over L is dq over 2. Isn't this really the same kind of question? It's still going to have an ln. It's still going to end up with an e to the, right? So what should I write next? ln absolute L equals, no, the antiderivative of dq is q. So this is going to be q over 2 plus a constant. Now what? E to the, and you get L as a function of Q is B e to the Q over 2. So now the continuous growth rate is 0.5, that's all. It's like 0.5 Q instead of 0.02 T in the previous example, right? Now they gave you initial conditions, didn't they? L of 0 is what, 100? So let's figure out B. If you can figure out B, get a particular solution, that's good, that's preferred. So plug in what for L? The 100. And plug in what for Q? 0. So again, B is the initial population, whatever you want to call it. So L as a function of Q is 100 e to the Q over 2. Okay? Are we okay with that? Alrighty then. All right, let's just keep on going. Number 4. Just practice this up. Number 4 says dq dt, some quantity changing over time. Or, well, I'm not going to get into that. Equals q over 5. And the initial amount is q is 50 when t is 0, or you can say q of 0 is 50. This could be like, well, I'm not going to get into that. It's probably coulombs or something. Or charge. Yeah, coulombs and charge. Charge and coulombs. All right, anyway, how do you separate this one? Bring the q down and the t up. Is it always cross multiplying? No, it isn't. Okay. So dq over q, just get the q's together in such a way that you can integrate. dq's got to be in the numerator, equals dt over 5. Get all the t's on the other side. Well, this is the only t. Make sure dt is in the numerator so you can integrate. You can't integrate with dt in the denominator. You can't integrate with two different variables. How do you integrate this? This is just 1/5 of dt. You can write it this way. So all you're integrating is dt. What's that? T. Over 5 now. Same like before, over 2, right? Yeah. All right, so you get? Sounds good. Don't forget the constant of integration. You like C, go for it. I'm going to use A right now. And then what? E to the both sides. You get the initial condition was that Q is 50 when T is 0. So guess what B is? So again, exponential growth and decay curves, this is usually what happens. This is the initial amount. When you start off in the differential equation where the rate of growth of the quantity is proportional, 1/5 of the total quantity, you're going to have exponential growth because the 1/5 is positive. All right, 5's on the homework. 6. Five, 10, 15, 20, okay. Let's see. Homework tonight is going to be 11.4, 11.5, okay? We're going to do some 11.5 later. Number 6 says P dp dt is 1. And P of 0 is 1. How are you going to separate this one? It's actually one step. Just bring the dt up, right? Okay, so multiply both sides by dt. And now is this an ln problem? Is it? Really? No? It's ln if it was dp over p. This is different. How do you differentiate, anti-differentiate this? No, that'll mess it up. They'll get the p's mixed with the t's again. This is good. This is ready to integrate. How do you integrate p dp? This is not the toughest question you've seen. You've seen this a million times, believe it or not. No, not just p. P squared over 2, because this is p to the 1 dp, right? You know how to anti-differentiate u to the n to u. You get u to the n plus 1 over n plus 1, right? So p to the 1 dp is p to the 2 over 2. So you got p to the 2, or p squared over 2, equals t plus some constant, okay? Sometimes you get a million constants, so I'm not going to start with c. All right, so, well, that's fine. But can you get p alone? What do you do to get p alone? Multiply by 2. P squared is 2t plus some other constant. It happens to be 2a, but I don't care. It's some constant. All right, it's still p isn't alone really. Square root. P has two possible answers, a positive and a negative principal root of 2t plus b. Now they gave you an initial condition. P of 0 is 1. Does it matter? Let's see, we're probably getting two different curves. Remember, the solution to a differential equation is a function whose derivative they were describing, right? So I really have two solutions here. I have P is the positive principal root, and P is the negative principal root. If you put them together, I think you get some sort of a parabola. But you can't put them together and get a function. Yeah? Well, how would it come out? The square root of the sum is not the sum of the square roots. Yeah, it's not going to come out like that. The square root of a product, you could. If it was 2bt square rooted, you could bring out rad b if you wanted. If that helps, if it's b is a perfect square or something. Anyway, so let's plug in stuff. P of 0 is 1, so plug in 1. And plug in 0. And b is, well, 2 times 0 is 0, plus b is b. Rad b is 1. If rad b is 1, well, b's got to be, now I'm squaring. To get rid of the radical, I'm squaring, so there's a unique answer, 1. All right, now does it matter here? Is b different? Let's find out if b is different over here. Plug in 1 now, and 0. B might be different, I don't know, I'm just being careful here. 2 times 0 is 0, plus b is b, rad b is that. What happens if you square both sides now? You still get 1, right? Don't you? If you square a negative? So you still get 1, right? So sometimes you get a different b if you have different, right? Be careful. So I really didn't have to separate this out. B is 1 no matter what. So my solution really is P equals plus or minus rad 2t plus b, but b is 1. But realize that's two different functions. That's two curves, two solutions. If you graph positive rad, if you graph negative rad, it's two different curves that solve the same equation. Okay? All right, any questions through 6? Practicing variable separable. That's it, yeah. Wait, speak up what? Because I'm squaring both sides to get rid of the radical. When you square a negative, it's going to be positive, right? A negative times a negative is a positive. When you square something, you multiply by itself. No? I thought so. What? I'm just doing the same thing I did on the left side. I squared rad b, I got b. I squared 1, I got 1. I squared negative rad b, I got b. What's negative rad b times negative rad b? It's a negative times a negative is a positive. And rad b times rad b is b. As long as b is positive, otherwise b, that's an absolute value. All right, let's not get stuck in algebra here. 7, believe it or not, is exactly like 1, 2, 3, 4, 5. 8 is exactly like 1, 2, 3, 4, 5. 9 is exactly like 1, 2, 3, 4, 5. This is getting boring. Because you put 10 is exactly like, well, that's on the homework. 1, 2, 3, 4, 5. You bring the m down, the m over m, right? Let's see if we can find something different. 11 is different. Okay, let's do it. I'm getting sick of doing the same problem 50 times. Realize when I did 1, 2, 3, and 4, they were all really the same thing. That ln stuff and the e to the stuff. I don't want to do that all day. All right, so 11 is a little different. Let's see what we can do here. 11 says that 2 du dt, or u prime, remember u prime means time derivatives, equals u squared and u of 0 is 1. So how do you separate the variables now? Switch them, right. In other words, bring down u squared and bring up dt. Is that okay? All right, so I got 2 du over u squared equals dt. Now, I could leave this 2 here, but I sort of like to leave those constants over there. I'm going to divide by 2. You don't have to. You'll get the same answer if you do it the other way. Now, how do you anti-differentiate this? Is this ln? No, this is ln. This involves an antiderivative with ln in it, right? But this is not. What is this? How do you anti-differentiate that? What rule? We know a rule for it. Not quotient rule. We don't know a quotient rule. There are several quotient rules. Tune in Calc 2 for integrating. No? What if I wrote it this way? Can you do it now? Same thing, I didn't change anything. 1 over u squared is u to the negative 2. How do you integrate u to the n du? U to the n plus 1 over n plus 1, you know this. So what's n plus 1? So you get u to the negative 1 over negative 1. What is that really? Without the negatives. Negative 1 over u, right? Now let me write it that way. So that's negative 1 over u equals what? T over 2 plus. By the way, do you realize why they always say plus c in the book? This is why. Are you ready? This is silly. Because you technically, we're sort of glossing over this, technically there's a constant of integration here and here. So why don't you combine them all together? If you subtract a from b, that's why they always say plus c. So you don't have to do the constant of integration on both sides because they can always combine on one side. And that's why they skip the a and the b and they go to the c right away. That's where the plus c comes from. I mean, it has to be a constant. That's not what I'm talking about. Why did they call it c? Because they skip this a, b stuff, right? Anyway, can we get c? Well, I think they gave us initial condition. Yeah, u of 0 is 1. So plug in 1 and 0. So negative 1 over 1 equals 0 over 2 plus c. So what's c? C is negative 1. So let's go back to the general solution. It's this guy. Negative 1 over u equals t over 2 minus 1. Okay? Negative 1 over, yeah, that was great. Over u is t over 2 plus c, but that's a negative 1, so minus 1. Yeah, am I done? Not really, because I want to get u alone in the numerator. Don't I usually get u alone in the numerator, or p alone in the numerator, or y alone in the numerator? This ain't it. This is a solution. This is a general solution. This is a particular solution to this problem. But I want to get u alone. How do I do that? Multiply everybody by negative 1, get rid of... You could. Do I have to? I'm not sure if I have to. I'm going to lay off of that for 1 second. What? Multiply by u. You could. Yeah. But if you multiply both sides by u, it doesn't help too much. I'm thinking, could you make this a cross multiplication problem? You could do that. Yeah, there's a lot of ways to go with this, but couldn't I actually add or subtract these two fractions? If it's not a fraction, you can always put it over 1, right? What's the common denominator now? 2. So multiply top and bottom by 2. So isn't this really t minus 2 over 2? Which you can cross multiply? One step to get u alone. One more step to get u alone. What? So u is negative 2 over t minus 2. Now guess what? If you check this with with Bob, is this a Bob question? 11, yeah. I bet you Bob doesn't write this. I bet you Bob writes this, and you're going to get all conflustrated checking your work. Isn't it the same thing? If I multiply the top by negative 1, I get 2. If I multiply the top by something, I better multiply the bottom by something, or I've changed the number, right? If I multiply top by negative 1 and bottom by negative 1, I'm really multiplying by 1. Is that okay? But when I multiply by negative 1, I'm talking about the opposite. What's the opposite of a difference? It's changed the order of the subtraction. Or the opposite of t is negative t, and the opposite of negative 2 is positive 2. This is probably what Bob says. Was there a question I missed? Ann? Somebody? That's described, that derivative describes. The derivative in that equation? Yeah. You're starting off with an equation that has some sort of a derivative in it. Right? U prime. The idea is to get rid of the derivative and just get u. If you can. Okay? I'm just curious, just for fun, what does Bob say? I bet you anything Bob didn't write it this way. Just for fun. What is this? 11.4, number 11? I never talked to Bob. Back of the book. 11.4, number 11, and... Oh, Bob, you're really weird. Bob did that and divided everything by 1/2. Divided everything by 2. Stupid Bob. Okay. What if you divide top and bottom by 2? What do you get down? The numerator is 1. The denominator is 1 minus t over 2. That's what Bob did. Not only did Bob switch up the signs, he got rid of the 2's. Why? Don't know. You don't have to do that. If it makes sense in the context of the problem to do that to simplify things, great. But there's no reason to do that here. All right, questions up to here. Practice, 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 variable separable. And it's going to involve some u substitution. Have we done any u substitution yet? No, we haven't. Ooh, we better get to some like that. Let's see. Well, let's just play around here. What about number 12? No u sub yet, just crazy variable separable, right? All right, dz dy is z times y. And z is 1 when y is 0, or z of 0 is 1. We're trying to find z as a function of y. When y is 0, z is 1, right? How do you separate this? You're going to write dz, what? Over z equals y dy. All right, this is integrable on both sides. What do you get for this antiderivative? ln absolute, no, don't do that. Don't do that. ln absolute z equals, now don't get flustered here. You know this, y squared over 2. Okay, now what are you going to do? Are you done? I want to get z alone if I can. This is a general solution, but I want z alone. And then I want the particular solution. If I can get it, I got to figure out a or b or whatever I got. So what do you do to both sides? Raise as powers of e, right? E to the, and you get z as a function of y is b e to the y squared over 2. Okay, can you resolve b? I think it said when y is 0, z is 1. Yes, it did. So here's 1, and here's 0. 0 squared is 0 over 2 is 0. E to the 0 is 1, so b is 1. Yeah. When you do the e to the thing, remember that e to the sum is the product of e to the first addend times e to the second addend. So this is just some constant. I figured I'll call it b. Because I don't care that it's e to the a. I don't want to figure out a. That's complicated if it's e to the a. But this is easy. B is 1. Boom, done. So B is 1, and your final particular solution is Z is 1 times e to the y squared over 2. Questions? Yeah. Well, when we plugged in the initial conditions, it said in the general solution, we plugged in Z is 1 and B is 0. Z is 1 and y is 0. To get e to the 0 is 1 times B is that 1. Okay? Okay. All right, practice, practice, practice. All right, here's an important pattern too. Questions 1, 2, 3, 4, and 5 were all about exponential growth and decay. 13, 14, 15, 16, 17, 18, 19 are all about Newton's law of heating and cooling, or exponential approach. Remember Newton's law of heating and cooling? If you take out a Coke out of the fridge at, I don't know, 40 degrees Fahrenheit, and you put it on the table in room temperature, over time, what's going to happen to the temperature of the Coke? It's going to go asymptotically to room temperature. Remember we talked about this. What if you take out a turkey from an oven? It's 400 degrees Fahrenheit. And you bring it out on the table at 68 degrees Fahrenheit. What's going to happen to the temperature of the turkey? It's going to approach asymptotically room temperature from 400 down to 68. That's this kind of differential equation. Look at number 13. dy dt is proportional, and they give you the concept of proportionality in this case, to the difference of the current y and 200. All right, now this could be a turkey problem. If 200 is the ambient temperature, I guess that's room temperature on Mars in noon on the summer's day in Celsius. That's room temperature on Mars, sorry. It gets really hot at noontime on a summer's day at the equator on Mars. It gets really hot. All right, so assume you're cooking turkeys on Mars, right? What if you pick a value, your turkey, what if it starts off with a temperature greater than 200? It's going to be a positive rate of growth. What if we start with a temperature less than 200? It's going to be a negative rate of growth. So is this Newton's law of heating and cooling? It isn't. This would be, but it's similar. Now, if you plug in an initial condition where the temperature is more than the room temperature, say that's room temperature, right? Now, if it's more than, this rate of growth is positive or negative. If y is more than 200, the rate of growth is negative. That's Newton's law of cooling. It's going to cool to 200. What if we plug in an initial condition less than 200, like 10 degrees? This is going to be positive. It's going to be positive throughout until you get to that asymptote, okay? So this is what Newton's law of heating and cooling looks like, okay? If this is the 200, if you start less than 200, it's going to go like this. If you start more than 200, it's going to go like this. But that's not what they gave you. They gave you the opposite sign. So where this was increasing, now it's going to be decreasing. Where this was decreasing, now it's going to be increasing. So it'll look like this instead. If you start with a temperature less than 200, it's going to decrease. If you start with a temperature greater than 200, it's going to increase. But this is what's known as exponential approach. Remember exponential decay, what does it decay to when you have like a radioactive isotope, carbon-14, and it decays over time? How much do you get as time goes to infinity? It gets smaller and smaller and smaller and smaller, and it goes asymptotically to what? 0. This is like that, except it's not approaching 0, it's approaching 200. So it's called exponential approach. Rather than approaching 0, it's approaching something else. So when it's approaching this, okay, it looks like Newton's law of heating and cooling. When it's not, when it's this one, it's not heating and cooling, it's something else. Notice, what if you plug in 200? What if you start at 200? What happens? Your initial condition is y of 0 is 200. So what happens? What's the growth rate dy dt when y is 0? Y is 200. 0. So if you start at 200, you're stuck at 200, right? Okay, so that's called the equilibrium solution. If you start there, you're stuck there. That's an equilibrium solution, right? This is known as a stable equilibrium. No matter what you do, you're trying to get to the 200. This is known as an unstable equilibrium. No matter what you do, you're going to get farther and farther away from the 200. This is this. This is this. But they're very similar. The equations, you solve them the same way. Okay? So this is Newton's law of heating and cooling. This is something completely different. Ugh, it's not heating and cooling. It's something weird. I don't know. Okay? So let's solve this thing. 13. Let's start over again. So now that you know what the differential equation is modeling, let's solve it. dy dt, the rate of change of y over time, whatever y is, it could be temperature, I guess, is 0.5 times y minus 200. And y is 50 when t is 0, or y of 0 is 50. Okay? So how do you separate this? What do I write? dy, what do you think? Over y minus 200 equals what? It's 0.5 dt. Both sides you know how to integrate, don't you? Technically, well, okay, you tell me. How do you integrate that? Is that an ln? It is if you do u substitution. Who's u on the left side? Y minus 200. Who's du on the left side? If u is y minus 200, du is negative, it's not negative, it's just d1 dy. So that's u, sorry, that's du and that's u. So we're doing ln, right? Okay. So you need u substitution here, technically. So this is the ln of absolute y minus 200 is equal to what? 0.5 t, or t over 2 if you like. You know what? I'm going to write it that way. Plus a constant. Now what are you going to do? E to the both sides. So e to the this, e to the this. And what do you get? Y minus 200 equals b e to the t over 2. And how do you find b? Well, they told you to plug in y is 50 when t is 0, and e to the 0, or 0 over 2 is 0, and e to the 0 is 1. So b is the initial temperature difference, or whatever it is. So what's b? Negative 150. So b is negative 150. So let's put that all together in this general solution. That's your general solution. Y minus 200 is negative 150 e to the t over 2, which is fine, but can't you get y alone? How do you get y alone? Add the 200. So how about I write it this way? Y is 200 minus 150 e to the t over 2. Notice what this is doing. What? Make it, no, those are not like terms. You can only subtract like terms. If this was 200 e to the t over 2 minus 150, then I could do that. But this is just a constant and this is not. Notice what solution I got. I got this one. Because I started with this, which was an unstable equilibrium, at a point, y is 50, less than 200. So it's 50 and then gets more and more negative. Isn't that what we got? What happens to e to the t when t gets huge? As t gets bigger and bigger, e to the t gets really big. Times the negative 150 becomes more and more negative. So it's 200 minus 150, 200 minus 300, 200 minus 3 million, 200 minus 3 billion. It gets more and more negative. So it indeed looks like this curve. This is what we just got. One of these curves. You could get one of these, you could get one of these, you could get one of these, you could get one of these. We got this one. Okay? Alrighty. Questions on 13. Alrighty. Believe it or not, 15, 16, 17, 18, 19 are all the same. So let's do one of those. How about 16? They're like this, okay? What made this one easy is that they factored out this constant, okay? Keep that in mind. They factored out this constant. Keep that in mind. Look at 16. dq dt, some quantity changing over time, is equal to 0.3 q minus 120. And q of 0 is 50. Can you find q as a function of t, the particular solution? Isn't this the same thing? Except you want to factor out what? 0.3. Now remember, factoring is just dividing. If it divide everybody on the right side by 0.3, what's left? If I divide this by 0.3, I get 1q, right? What if I divide 120 by 0.3? Well, that's 3/10, right? So 3 into 120 is 40. How do you divide by tenths? You multiply by 10. 400, right? Is that what you said? 400? And it's still negative? Okay. This is more easily separable if it's in a factored form. So that's the hint from question 13 on how to do question 16. Otherwise, it's really the same kind of question. Okay? Now think of it. If you start with a value equal to, what makes the dq dt 0? What makes dq dt 0? If you plug in q is 400. So that's your equilibrium solution. Now, is it a stable equilibrium? Are we going to get closer and closer to 400 from below or above? Or is it an unstable equilibrium? We're going to get farther and farther away from 400 as t goes to infinity. Well, if I plug in a value bigger than 400, like 500, what's the growth rate? Positive or negative? And it's always going to be from then on in, because the only zero is when q is 400. So it's going to get bigger, bigger, bigger positive, right? What if I plug in a value, an initial condition less than 400, like 50? This is going to be positive or negative? Negative. And the only zero was when you had 400, so it's going to get more and more negative. So is it exponential approach from above? Is it exponential approach from below? In other words, Newton's law of cooling or heating. Or is it an exponential approach problem which is unstable rather than stable? It's unstable. And now, is it going to go more and more positive or more and more negative? More and more negative. Just like the last one. It's really almost the same as the last question. Okay, so let's try this. Just like 13. Right, because it's y minus something. And it's q minus something. It's the same idea. All right, so separate this thing. dq over q minus 400 equals .3 dt. All right, and to differentiate both sides. Whoa, what the hell happened there? All right, so what do you get? Who's you? q minus 400. Who's du? dq. So isn't this 1 over u du? So I had to differentiate 1 over u du, you get ln u, ln absolute u. But u is q minus 400. When it's a straight u sub, you don't have to multiply and divide by something. I just do it. Do you want to write it out? That helps you? Go for it. It's fine. Equals 0.3 t plus something, right? Some constant. All right, what are you going to do now? E to the. And what do you get? Stop doing that. 0.3 t. Okay. Now, how do you get the b? They gave you initial conditions, right? They said plug in q is 50 when t is 0. So e to the 0 is 1, and b is the initial difference. b is negative 350. So let's put that back into the general solution. By the way, you could write this as q alone here too if you want, but that's fine for a general solution. So q minus 400 equals negative 350 e to the 0.3 t. It's doing it again. And just for fun, q alone, 400 minus 350 e to the 0.3 t. So if you plug in 0, you get e to the 0 is 1 times 350 is 350, and 400 minus 350 is the initial 50, right? If you plug in numbers bigger than 0, t gets bigger and bigger and bigger. This exponent gets big, e to the gets bigger. You're subtracting minus 350 times big begets more and more negative. Right? So that's an unstable exponential approach that's decreasing. Good? Not good? Questions? Okay, that's about as crazy as this gets. Let's see. Let's see if we can find one we haven't played with too much yet. How about 21? '21 says dz dt is equal to t e to the z. And your solution goes through the origin. In other words, z of 0 is 0. Stop doing that. Right? So z is 0 and t is 0. How do you separate this? dz over e to the z equals t dt. And you can integrate both sides if you think of this how. You're thinking u sub? Is that what you said? Not yet. Well, okay, what's u? No, not yet. Because if you make u e to the z, du is not dz. It's not a constant multiple of dz either. It's some complicated mess. You can only do your substitution if you end up with a multiple of dz. dz times 2, dz over 3, dz times negative 5, right? You don't. If u is e to the z, du is e to the z dz. It's too complicated. Too many variables. Not u sub yet. But you can make it u sub. Can you rewrite this? No, you're thinking ln still. No, same thing. What? That's e to the negative, right? It's e to the negative z dz. And then you know how to integrate e to the u. And u is, and it is a u sub. Right? Okay, here we go. So u is what? Since I know how to integrate e to the u du is e to the u, who's u? Negative z. If u is negative z, who's du? I think you said it. Say it. No. No, it's not just dz. Negative dz. Negative dz. That's going to make a difference. So I'm going to replace dz with negative du. So I'm really integrating negative e to the u du. How do you integrate e to the u du? You get e to the u. But don't forget the negative in front. So it's e to the u. But u is negative z. Okay. How do you anti-differentiate this side? T squared over 2. Okay? So now, can we get A? They said it goes through the origin. When t is 0, z is 0. So, let's plug in 0. By the way, I could rewrite this, couldn't I? What is this really? As a fraction, can't you? Negative 1 over e to the z. Let's write it that way. Just make it easier to play with. Negative 1 over e to the z. And by the way, we could get z alone if we want first, but I think I could get a while I'm at it. Plug in z is 0, so e to the 0 is 1, and negative 1 divided by 1 is negative 1. Plug in 0 for t. T squared is 0 over 2 is 0 plus a is a. We got a. Oh, okay. That was easy. A is 1. So here's your general solution, but z isn't alone. Negative 1 over e to the z, equals t squared over 2 minus 1, because a is negative 1, and I'm adding a negative 1, so minus 1. All right, how am I going to get z alone here? I want to get z as a function of t with z alone in the numerator if possible. Yeah? Not yet. ln won't cancel this. Yeah, ln won't cancel this, because this is negative e to the negative z. ln only cancels if there's nothing but a 1 in front. This is a negative 1 in front. Can't do it yet. It's a negative reciprocal is what it is, but how do you get the z out of this? You got to take the z out. How do you do that? I can't ln, no, not yet. What? I'm thinking cross multiply. We saw one like this. Can't you just subtract these two fractions? What fraction is this? 2 over 2. So it's t squared minus 2 all over 2? And now cross multiply and try to get the z alone. Negative 2 is e to the z times t squared minus 2. Yeah, that was good. Now what are you going to do to get z alone? This is just algebra now. Don't get tripped up with the algebra. Divide, right? So negative 2 over t squared minus 2 is e to the z. Okay, now you can ln both sides to get the z out of there. So you get the ln of negative 2 over t squared minus 2 is z as a function of t. And you're done. Unless you talk to Bob. Bob might say this. Well, actually, whoops, I got a little sloppy. Wait. No, I didn't. That's good. And this is fine. You want to stop here? You're done. But Bob might do this. Bob might actually do... Remember what Bob did last time? I think Bob did this, actually. Which Bob thinks is simpler. Just divide everything by 2. You want to stop here for your particular solution? That's fine. That works. You can graph that, play with it, do whatever you need to do. Okay? All right, so there's all kinds of weird stuff that can happen with variable separable and chain rule mixed together. Oh boy, what joy. Let's see now. How about 26? Okay, YouTube, I don't know if we're going to be able to finish this one with you. Let's see if we can. 26. says d omega d phi, no, d psi, sorry. I think they're talking Greek here, sorry. You can think of this as w and y if you want. Is equal to negative omega squared tan of psi, where omega of 0 is 2. Okay, can you variable separate this? D omega over omega squared, okay. D omega over omega squared. You want to say dw over w squared? It's a free country. But I think they're talking about omegas and stuff. Equals what? Negative tan of psi times d psi. That's it. Okay. Now let me think here. Can I integrate that and can I integrate that? I'm leaving the negative 1 out of it till later. Didn't we figure out the antiderivative of tangent yesterday? It had to do with ln because sine over cosine. ln of secant, right? Now remember when we first did it, we ended up with negative ln of cosine, and we took the negative 1 and brought it in as an exponent. Cosine to negative 1 was secant. Here we're getting negative ln of secant. So that's really ln of cosine if you want, without a negative. It doesn't matter. You can leave secant if you want. All right. So, but wait, how do you integrate this side? Not ln. This is ln. This is not. Right. So this is the antiderivative of omega to the negative 2 d omega is equal to negative the antiderivative of tan psi d psi. And if you have to figure this out as a u sub with an ln of based on sine over cosine, go for it. You're going to end up with ln of secant or negative ln cosine. What do you get here? Omega to the negative 1 over negative 1, but remember, what is that really? Negative 1 over omega, might as well write that? Okay. So that's negative 1 over omega is equal to negative, what did we say? ln absolute secant of psi plus a constant. Okay? We okay with that? No? We figured out yesterday that the antiderivative of tan u du is ln secant u. This is u. This is the power rule. Omega to the negative 1 over negative 1. I'm adding 1 to the exponent, dividing by what I get. No, this negative is still here. That negative came from, well, this is where it came from. U to the n plus 1 over n plus 1. There's a negative, right? Okay. All right, but it's easier to deal with if we write it this way. Okay? Now, you can get A now, or you can get A later. It doesn't matter. By the way, the negatives, you could cancel them if you want to multiply both sides by a negative. Why not? All right. Can you get A? What was the initial conditions for 26? Omega of 0 is 2, so plug in 2 for omega. And I'm about to lose you too. 1 over 2 equals the ln of the secant. And they said plug in what for psi? 0? Okay. But what's a secant of 0? Isn't it 1? Because secant is 1 over cosine. And cosine of 0 is 1. So 1 over 1. Right. And what's ln of 1? 0. So you get that A is 1/2. All right. So here's your general solution. Here's your particular.